In this video, I'll show you how ellipses show depth, and it's in my book, Ellen's Guide to Perspective, on Amazon. I'm going to quickly review common four-sided polygons before I start talking about ellipses. So to find the center of a polygon with an even number of sides, you connect opposite corners. So for a square, which has equal sides, these diagonals divide the corner into two 45-degree angles. A rectangle has two pairs of parallel sides, and the diagonals do not form 45-degree angles. A parallelogram has two pairs of parallel sides, but the angles aren't 90 degrees. And a trapezoid has only one pair of parallel sides, and the other two usually converge, and the diagonals meet more toward the short end than the long end of the trapezoid. And that's different from these, where the diagonals meet at the center of the form or the shape. Now, for a symmetrical polygon with an even number of sides, diagonals connecting opposite corners intersect in the middle, even if the sides aren't equal, like these hexagons and octagons in perspective. However, this method does not work if the diagonals don't cross or if the polygon isn't symmetrical. So far, we've discussed polygons with an even number of sides. These are polygons with an odd number of sides. So how do you find the center? You connect a corner to the middle of the opposite side. And if all the sides are equal in length, then this line is perpendicular to the side. Here's a pentagon. We connect a corner to the middle of the opposite side, and this line is perpendicular to the side. Now, this method works for some polygons without equal sides, but not for others like this one. A better approach for this one is to use horizontal and vertical lines. For the house shape, the peak of the roof should lie vertically above the center of the rectangle. I'm now going to talk about a circle and a square, and my next slide's about an ellipse in a rectangle. And then finally, I'll end with an ellipse in a trapezoid, which is the basis of ellipses showing depth. So it starts a little elementary here, but try to stick with it because the end is good. So let's look at a circle in a square. A circle can be completely enclosed only in a square, and it is tangent to the middle of each side of the square, only at these four dots. Using a square then makes measurements and divisions of circles easier. The diagonals of a circle are the same length here and are perpendicular to each other, and they bisect the right angles of a square, making two 45-degree angles, and that becomes important in perspective. The artist can use the intersection of the diagonals to find the center of both the square and the circle it encloses. Now, if you connect the blue dots, which are the intersections of the diagonals with the circle, you'll get a square inside the circle, with sides parallel to the large square, all sharing the same center. So if you have a square, you can easily make a circle, or vice versa. Now, the lines connecting the middle of the opposite sides of the square are the same length and are perpendicular to each other, and the circle touches the square at the ends of these points, these green dots. Now let's discuss ellipses in a rectangle. Only one ellipse fits into any particular rectangle. The ellipse is tangent to the middle of the sides of the rectangle. The diagonals of the rectangle meet at the geometric center, which I'll describe in a bit. They can't be perpendicular, nor can they bisect the right angles of the rectangle, because if they did, then the rectangle would have to be a square. As the rectangle elongates, angle 1 gets larger and angle 2 here gets smaller. If you connect the blue dots, which are the intersections of the diagonals with the ellipse, you'll get a rectangle inside the ellipse. And then you can draw another ellipse inside this rectangle. So once you have one ellipse, you can draw rectangles and vice versa. Lines bisecting the sides of the rectangles are perpendicular to each other and meet at the geometric center. And they divide the rectangle into mirror images. So this look of an ellipse in a rectangle appears flat, so it cannot represent a circle in perspective, which only looks like an ellipse but is in fact a circle. And so for that, we need trapezoids. This shows the relationship of an ellipse to a trapezoid, and this is the essential part of perspective. The ellipse is tangent to the middle of the back and front of a symmetrical trapezoid, but not to the middle of its sides. Instead, the lower part of each side is longer than the upper part if we view the trapezoid as a flat shape. But if we think of it as directed front to back, then the front part of each side is larger than the back part, and that's diminution with distance, getting smaller with distance, a depth cue. The further back these purple dots go, the more the sides of the trapezoid must angle away from each other so they remain tangent to these dots. The ellipse is still the same geometric shape, just visualized differently. Its most prominent curve seems to be in front, while its back seems flat. And that explains why distant shorelines look straighter than the shore nearby. The diagonals of a trapezoid meet at the perspective center, the center of the whole image, like the center of a pizza or where the hands of a clock meet. The center moves back as the sides increasingly diverge, and this will be very important. To draw a trapezoid inside the first one, find the intersection of the diagonals with the ellipses, these blue dots, and connect them together, and you get a trapezoid which geometrically isn't the same as the large one, although they both converge toward the same vanishing point. This smaller trapezoid can enclose another ellipse, like that, forming concentric circles in perspective, where the inner ellipse is pushed back. So the perspective center of the trapezoid, the yellow dot, is where the diagonals of the trapezoid meet, and that's the center of the whole image. It is behind the geometric center of the ellipse, which is the red dot, where the major and minor axes meet. The green horizontal line through the perspective center divides the ellipse so that the part in front appears larger than the part in back. In contrast, the geometric center of the ellipse divides the ellipse into two equal parts, so it is rarely used because it doesn't suggest depth. And as the sides increasingly angle away from each other, these two centers, the yellow and the red center, get further away from each other. Remember my book, Ellen's Guide to Perspective, on Amazon, and please remember to subscribe.